Started. So I'd just like to say hello to everyone and welcome to the fourth session of our fall program for VISIM. And so today, Ajay, Baniya, and Sandra Milev will be presenting their work. So each presentation should be about 20 minutes, and then we'll have a chance for Q&A after each presentation from the audience. So again, thank you all for attending. And so our first speaker is going to be Ajay Baniya, who's a registered professional engineer and structural engineer in the state of Nevada, and he has more than 5 years of experience as a civil or structural engineer, and about 3 years of research experience as a graduate research assistant. He completed his MS in structural engineering from the University of Texas at Arlington, and currently he's been doing research on the durability performance of CFRP composites subjected to environmental conditioning and fatigue stresses for over 2 decades. And his research interests include CRFP composites, machine learning, fatigue stresses in steel bridges, seismic engineering, and building information modeling. So with that, I'll ask Ajay to please share screen and present. Thank you.
Good afternoon, everyone. Thank you very much, Adrian, for the introduction. I'm hoping everybody can hear me.
Yes.
And thank you very much, everyone, for attending this virtual session. This is a really good opportunity for me to present my work in this virtual session organized by Northwestern University. A quick introduction again. I'm Ajay. I'm a PhD student at University of Delaware. My today's presentation is based on the research I did in year 2021-2022 under supervision of Professor Yovan Tatar. The topic of my presentation is durability assessment of FRP composites, repairs in the bridges. I'll start the presentation with a brief overview of FRP composites, then discuss the motivation and objectives of the research. I have summarized multiple test procedures conducted in the laboratory and in the field. I'll go through them one by one and followed by the results and conclusion. A quick introduction on current status of the infrastructure in the country. Current data shows 7.5% bridges in the country are structurally deficient. And as you can see in the pie chart, 39 and 15, more than 54% of the bridges are aged 40 years and more. The need for repairs and retrofitting is already very high, and it's growing faster. So the Department of Transportation and engineers are always looking for new and innovative technique to strengthen the structures. CFRP composite is one of those innovative technique that has been widely adopted in the industry to strengthen the structure, especially the structures in transportation or bridges. Just a quick overview on CFRP composites. CFRP stands for carbon fiber reinforced polymer. It's made up of fibers and matrix. There are different types of fibers, and carbon fiber is one of them, frequently used in the civil engineering application. Matrix are sometimes called resin or just epoxy, depending on who we are having conversation with. And the use of the matrix is to bind the fibers, transfer load between fibers, and also provide protection to the fiber and overall integrity of the composite. And fibers are typically responsible for the strength and stiffness of the composite. What makes CFRP composite well suited for the civil engineering application? The first reason is the material itself is alkaline resistant and non-corrosive in nature. And if we see the plot, density versus strength plot for various materials, as you can see, density goes higher if we go right, and strength goes higher as we go up. As seen in the plot, composites are less tensile than the mild steel and has more tensile strength than the mild steel. CFRP composites are 5 times lighter than steel and 8 to 10 times stronger than steel in tension. So that's why CFRP makes a really good candidate for the strengthening purpose. As I mentioned before, CFRP has been widely adopted in the industry, but despite uses of CFRP composite in the industry for quite some time now, we still do not have design guideline that addresses the design requirement of CFRP to the steel substrate. We do have some design guideline that addresses the requirements for CFRP and concrete, but we do not have any for CFRP and steel. And given the short history for this material, only about 30 to 35 years now, we still do not have enough data that warrants the long-term performance or durability performance of CFRP. So overall, the objective of this research is to assess the durability performance of CFRP after 22 years of service, and also make use of the field data to evaluate the CE factor. CE factor is an environmental reduction factor, which is typically determined using the accelerated laboratory test, and the field data we'll be getting from this bridge will be used to verify if the factor is enough adequate. For this research study, bridge 1704 was selected. The bridge shown in the right is located in New York, Delaware, and it's about 2 miles south of the University of Delaware. The bridge is made up of steel, acting non-compositely to the concrete deck, CFRP. Composites were installed to the girder 5 only, just for the purpose of demonstration back in 2000 by Miller. So that's like 22 years of service as of now. And there was no purpose other than just demonstration purpose. CFRP was not required for improving the structural integrity of the girder or the overall bridge section. Here are some more details on the CFRP composites. As you can see on the left, the section view shows the bottom flange of the W24/84. CFRP composites was attached to the bottom flange, making use of structural adhesive, and they used glass fabric to act as a barrier in between CFRP composite and the steel surface. So glass fiber, what it does is it prevents from the galvanic reaction, thus protects from galvanic corrosion. And on the plan view, we can see that the span of the girder was about 25 feet, and the overall length of the CFRP was 20 feet. It's important to note that 2 different types of structural adhesives were used. A northern half of the CFRP was attached using Plexus MA55 type structural adhesive, and the southern half had SIVA AV8113 structural adhesive. Now let's go to the various tests we conducted. We did some field tests, we did some laboratory, and some of the testing that run in the field were, the first we conducted structural health monitoring before performing any test or any sample collections were done. 3 transducers were installed on the midspan of the girder for 14 days to monitor the peak strain events due to the truck events at the sampling rate of 100 hertz. 100 hertz was just enough to record 25 data points per the crossing of the truck at the speed of 70 miles per hour. And secondly, we conducted some pull-off tests along the length of the girder to evaluate the bond strength and tension. The steel dollies were installed as shown in the figure, and they were allowed to cure for some time. This pull-off tester was used to detach the dolly or puck, and the force was recorded on the device. And from that force, we were able to determine the bond strength and tension. Enough samples were collected for various tests in the laboratory. It's a rigorous process. The sample collection is again a whole different presentation, but if you have any questions regarding the collection process, I'll be happy to answer after the end of the presentation. We ran additional tests in the laboratory to understand the degradation of the CFRP composites in micro level. We started with the spectroscopy test to assess the chemical degradation in CFRP. Similarly, we also ran dynamic mechanical analysis test, DMA, and differential scanning calorimeter, DSC, to determine the glass transition temperature of the matrix of the CFRP and the structural adhesive. All these tests were run on both control and field samples. They were run on both control and field samples, except for the DSC, because we did not have controlled sample. So we only had to run for the other samples. And I'll come back to the explanation of what TZ means and what is the significance of TZ in the upcoming slide. More tests were run in the laboratory to determine the mechanical properties of the CFRP composites. We ran 3-point bending test and tensile test to find the flexural modulus, tensile modulus, and tensile strength. And again, these tests were run on both field and control samples as well. The virtual inspection, the visual inspection of the bridge was conducted throughout the year of 2021. And it's seen in the left 2 figures. During the initial inspection, we did not see any signs of degradation. We saw some signs of degradation, as you can see on the right, but those were due to sanding or grit blasting of the CFRP while repainting process. And I think it's really important for bridge owners to understand the vulnerability of the CFRP and thus making the inspection process, if they don't already have in place, to avoid such mistakes. Then we, like we discussed earlier, initial inspection did not show any signs of degradation, but when we collected samples, we saw some hints of corrosion inside the CFRP. From the northern end of the beam, the corrosion extended for 6 feet inward. We also did periodic inspection during the year of 2021, which actually did not show any signs of rainwater or de-ice ingress through this northern end of the beam of the composite. The glass fabric that was installed to prevent the galvanic corrosion was found to be unsaturated at the location of the corrosion. So it was suspected that the corrosion was due to galvanic reaction. And then pull-off tests were conducted after completion of structural health monitoring. It was observed that 16 out of 20 tests, 20 tests did not reach the failure. The maximum capacity of the pull-off tester was 1145 PSI, which implies the bond strength and tension was more than 1145 PSI. And we do not have design guidelines that we can use to compare the minimum limit for the steel substrate. So the best we could do was to compare that with the requirement of some coating materials, like North Carolina had some requirements for zinc and aluminum piners, and we compared that data, and 1145 was significantly higher than the requirement for the coatings. And unlike 16 tests, 2 out of 20 tests, 10% fell prematurely below 50 PSI. And upon inspection, we saw that the reason was due to the air bubbles and inadequately saturated glass fiber. And these typically happen due to improper workmanship. So this is one of the lessons to be learned from this test as well, and for the upcoming installation process. Then we moved forward. TZ of CFRP matrix were determined using DMA tests, like I discussed before. And coming to glass transition temperature. Glass transition temperature is a range of temperature at which a polymer changes from one state to the other state. So it changes from hard or glassy state to soft or leathery state. What does that really mean? It's in simple words, TZ actually needs to be higher than the service temperature, because what happens is as the temperature goes high, the stiffness and the material strength decreases significantly. So we need to make sure the TZ is always higher than the service temperature or the maximum service temperature. And from the test, we found out that the field sample, the TZ of the field samples was reduced by 9% as compared to the control samples. Moisture causes, so basically the reason behind the reduction in TZ could be because of the ingress of moisture. What moisture does is it typically initiates 2 phenomena. One is the plasticization over short-term conditioning, and the other one is hydrolysis over the long-term conditioning, which eventually softens the material, causing the loss in stiffness and strength of the material. And we compared the values we obtained from the field with the minimum temperature requirement of ASTO, which was still greater than by 40%, which was good. This 57 comes from ASTO, which is the minimum TZ needs to be more than 40 Fahrenheit than the maximum service temperature of the bridge. So in our Delaware, the service temperature maximum reached up to 35, and based on that, we found this 57 degrees Celsius. Unlike DMA test for the matrix, we're not able to use DMA to determine the structural gas transition temperature of structural additive, because these samples were tiny and in powder form, so we were not able to run DMA to find the TZ for these samples. We had 2 different types of samples, MA555 and AV8113. And for both of them, we saw significant reduction, as you can see, 103 to 48, 90 to 36. But these numbers came from the literatures, and we're not able to find out the proper cure phenomenon of the control samples. So the apple-to-apple comparison in between control and field, we're not able to do that. Typically, what happens is when the TZ is this high, it's potentially due to the control curing, but at the same time, we do not have any information, so we really can't make any judgment based on that. The TZ for field samples for both structural adhesive MA555 and AV8113, both less than 57 degrees minimum requirement, which is concerning. And then we ran some spectroscopy tests. We ran tests on two control samples, C1 and C2, and then we also ran tests on field samples F1 through F39. We found some differences in 700 and 1508, but the intensities of the peaks, as you can see, were really less. So it signifies no evidence in chemical degradation. Then we moved forward with tensile modulus determination using the tensile test. We found out that this setup was used to determine the tensile modulus for the coupons that we collected from field and control. It was observed that the modulus of field samples was reduced by 15% control compared to the control samples. The reason behind the reduction could be environmental conditioning, but it was not possible to quantify the effect just done by the environmental effect. It's really important for us to tell that the extraction process of the sample and the preparation of the test sample for the test could have played some role in the reduction of modulus as well. ACI 440 does not really recommend the uses of environmental reduction factor for modulus determination, but on the contrary, from the test result, it seems like we might need to have something or further evaluation is necessary. More flexural tests were run to complement the tensile test. The modulus reduction obtained from 3-point bending test was comparable to that of tensile test. We obtained 15% reduction in modulus from the tensile test, which was 14% from 3-point bending test. And we also observed 75% flexural strength retention in field samples. However, ACI only recommends 85% retention. During the test, we found out the TZ of the matrix was reduced as well, which signifies the degradation due to environmental factors. So we can suggest that the environmental factor definitely played some role. But again, it's impossible to tell that whole 25% came from the environmental factors. We could have the same situation like before with the sample extraction process, preparation of test specimen, and fatigue loading in the field samples, especially for 22 years, and also the sustained temperature stress if it was there. Those things were not evaluated, so we cannot confirm that the whole 25% came from the environmental factors. The structural health monitoring was performed for 14 days, like I said before, and the peak strain event larger than 75 microstrain were recorded, and the current data and the past data was compared. So during the past 22 years, average daily truck traffic increased by 1.87 times, but at the same time, peak strain events increased by 3.17 times. So this signifies the degradation and stiffness property of possible degradation and stiffness property of CFRP composites. However, like I said before, we still have could have numerous other potential reasons. First one being the issues with concrete deck and support system, which we did not evaluate. And like we said in before, in the DSC test, the TZ of adhesive was found reduced, which as well could have affected the ability of CFRP to assist in the stiffness. And finally, from all these tests and observations, we conclude that CFRP does possess concealing behavior. During initial inspection, no signs of degradation was visible. More investigation, and we found there were some signs of corrosion from the previous studies. Galvanic corrosion was suspected. And this makes the visual inspection process challenging, and bridge owners should really consider the possibility of such galvanic corrosion or any other form of corrosion during the periodic inspection. From the micro level perspective, spectroscopy did not reveal any signs of chemical degradation. TZ of both matrix and adhesive was reduced, but the reduction in TZ of matrix was not as concerning as the reduction in TZ of adhesive. From overall, the mechanical properties of CFRP was found degraded after 22 years of service as well. And like I said before, it's not possible to quantify the exact contribution of the environmental effect. The modulus was found reduced by 15%, and based on that, 0.85 CE factor is recommended. However, more field test data is required to justify the recommendation. The CE factor of 0.85 on laboratory accelerated conditioning is already there for flexural strength, but it seems inadequate for the 25%. So we recommend at least 0.75 environmental reduction factor after 20 years of service life. And that's pretty much it. I'd like to thank Michael, Jason, Gary for all the help. And the research was sponsored by CMT, so many thanks to them as well. And thank you very much for the time. Please let me know if you have any questions. I would be happy to answer them. Thank you.
Great, thank you. Are there any questions?
So I have a little bit of a question. I think that these are nice results. Thank you for sharing. And these are not technical questions, but rather I think that from the standpoint of using these in practice, essentially, I wanted to get your opinion about where we might be in terms of commercial availability of these CFRPs to reinforce and I guess a repair these structures to prolong their service life. Do we have I mean, I don't know how available they are, how economical they are in particular.
So I think it's a really good question. From economy wise, I know multiple contractors who actually was really just doing the repair work using CFRP. CFRP material wise, it's not cheaper as compared to steel, just the material cost. But if you really compare it with the time effort, like, and let's say if I have to weld the steel beam, it's much easier to actually have CFRP installed because it just requires two different items. You can work in the field. You do not need heavy welding equipments and stuff like that. So that makes the installation process easier for bridges. And also at the same time, I have seen the application actually being used in the building industries as well. One of the important reasons I say that is because when we have CFRP, we can actually give the shape back to the previous shape. So it's not going to affect the shape of the structure. CFRP is really tiny. It has 8 to 10 times the tensile strength of the steel. Yep. I hope I answered your question.
Yeah, so this seems to be the future, which is cool. Thank you for sharing. Thank you for the nice talk.
Thanks, Joe.
So I had a question, actually maybe two questions. You showed a picture of some CFRP that looked like it, had been peeled off, maybe in like part of the, I forgot what slide it was on, but yeah.
Okay.
There, yeah. So I'm assuming that there it was done in the sense of like went out to inspect and maybe take samples.
Okay, so I think
yeah.
Please go ahead and ask your second question as well.
No, this question was like, does this peel off like that basically on its own? Is the bonding kind of like failing in that sense? Does this happen over this time period?
So this is actually not really typical, and this is from the other bridge after 22, 27 years of service on the concrete substrate. So this is just this is not the bridge that we evaluated this time. This bridge is located in Delaware as well. In our case, it was 22 years of service on a steel substrate, but this was 27 years. And the issues like this mostly happens with visible water, and if we have the UV, if it is really exposed to the sun, and those factors comes into play, humidity comes into play. And it also depends on if we have any coating, like, in case of the other bridge, we had paints to actually prevent the ingression of moisture into. In this case, we can see that it was not painted, so that could have also had some impact on the overall integrity of the CFRP.
Okay, I see. So in general, though, like after 20 years, is there a need to revisit these CFRPs and basically like reapply or like re-adhere these to the structure?
I think it really depends on if the CFRP is helping with the sustained loading or not. It really depends on that. If it is sustained, I think at that point you cannot peel it off and install again because it's already taking some stresses. At that point, you might have to retrofit. But typically, service life of 20 years, that's something, more research has to be done. We typically have design life of 75 years, but based on, we do not have CFRP for a long time, right? So this is 27 years is one of the longest ever, I believe so. And 22 years for steel substrate is also one of the longest we have seen in field. And we have seen good results in the steel, but we haven't seen as good result in the concrete. So it really depends on the inspection. I think we have to do more often periodic inspection to assess the condition in between.
Okay.
I worked also on this project, and my work was focused on this bridge that Ajay is showing the picture. So for this one, it was repaired in 1994, and the intention was to extend the service life of the bridge only for 10 years. And now it has been almost 30 years after. So I think in a way this was expected, especially as Ajay said, the surface was not coated, and there was a lot of moisture and water seeping through the joints and everything. So that is, and plus the concrete on this bridge was really in a bad condition. It was a lot of corrosion and cracking, especially longitudinal cracks. So I think that also overloading of the girders may have, caused some of these problems. Yeah.
Okay.
And for the cost, and I mean, they're not now so new materials. They're already used in many bridges. And for example, for this bridge, as the cost of repairing was 10% of the cost that would be paid for replacing this bridge that was in Delaware. Yeah. I also have a question for Ajay, because my literature review and everything that I did was more related to concrete bridges, and I don't know if you found more applications on steel and research how this CFRP works on steel.
I'm sorry, could you repeat the question again?
Did you find other examples of steel bridges that were repaired with CFRP?
So we do not have many bridges, but we do have some just research tests. Some of them had fatigue testing, loading, sustained loading as well. But specific to the steel bridges, there are very few. I saw some in some southern state in the US, but that was not the whole full-scale implementation as well.
And also these statistics at the beginning that you showed, do you know type of the bridges that are the most deteriorated and they have to be repaired? Is it, steel or concrete, or what type of
yeah, I think that breakdown would be really interesting to look into, but
yeah, because
this is actually the overall all in general in industry, overall industry, that's 7.5%.
Yeah, and last is a very technical question.
Okay.
Do you have a picture showing galvanic corrosion? Because I didn't notice that, and is okay. So this picture on the left, this is showing the steel below the FRP?
Yes, so after the sample was taken out, so this was taken for the tensile test, and after that we saw this. So that's why I mentioned that, the inspection actually could be misleading, because we did not see anything on the preliminary inspection, but after we took the sample out, we saw the degradation process, the corrosion had started.
Okay. Thanks, Ajay.
Thank you, Sandra.
Yeah. Thanks so much again, Ajay, for the great presentation.
Okay, thanks, Adrian. Thank you so much. Thank you so much for hearing me. I'll stop sharing the screen now.
Okay, great. Okay, so with that, our next speaker is Sandra Milev, who's a research assistant and a PhD candidate in the Department of Civil Engineering at the University of Delaware. Her research is related to the durability of FRP composites and self-healing polymers for application and construction. So I'm sure we'll hear some exciting other components of of her research.
Okay, so the topic of my presentation is polysulfide elastomers as self-healing sealants for transportation infrastructure. First, I want to talk about the motivation behind the research and what type of sealants I'm going to talk about exactly. So these sealants are used in construction joints to allow for thermal movement and prevent infiltration of water and incompressible material in rigid concrete pavements. And their service life is about 5 to 10 years. And after that, they have to either be replaced or repaired. So if that's not done, then water infiltrates inside the joint, and then it can cause erosion and faulting in the pavement and cracking. So the idea here is to develop a material, a sealant from self-healing polymer that will be used instead of conventional used sealants. And we expect that with this type of self-healing material, we are going to increase the service life of these sealants, and then reduce the cost of maintenance. This self-healing ability is enabled by the nature of polymer network. These so-called covalent adaptable networks are a new type of polymers. In general, all polymers are classified either as in two groups, thermoplastic or thermoset. Thermoplastic are made of these polymer chains that are just entangled, and bonds between the chains are very weak ionic bonds. So that means when they are heated, the chains uncoil and then they melt. So they can be, that means also they can be reshaped. But the problem with that is that they are not durable and the mechanical properties are not that good. On the other side, thermosets, they are made of polymer chains that are cross-linked. And these cross-links are actually covalent bonds that are strong, and that means that material is also has good mechanical properties and good durability properties and chemical resistance. But the thing is that when they are heated, they don't melt. For example, like thermoplastic, they just become softer and more rubbery. That means also that they cannot reshape or be recycled. So these covalent adaptable networks, they are designed to combine good properties of both of them. So the recyclability of thermoplastic and then good mechanical properties of thermoset. And this is enabled by the dynamic nature of covalent bonds. So what I'm talking about is that under certain triggers like heat or UV light, these bonds can break and then reform. For example, in this picture, if you look at these 3 units here, this bond here breaks in the end, but then another bond is formed between this one and this one, which means that through the entire time there is constant degree of cross-linking, but the topology of the network is different. So in particular, these polymers, these covalent adaptable networks that are triggered by heat are called vitrimers, and this is type of the material that we are going to use to make this self-healable sealant. These are some examples of the dynamic covalent bonds. One that was used a lot in the research is this transesterification. This is because it is applicable to epoxy resins that are widely used in construction. But the problem is that bond rearrangement is possible only at temperatures that are higher than 100 Celsius and also with a lot of catalyst. So the other example is this disulfide exchange. Good thing about this type of reaction is that it can happen at room temperature in ambient conditions and without using catalyst. It also, there are a lot of commercially available compounds that contain this disulfide bond. One key characteristic of these vitrimers is topology transition temperature. It is the temperature at which polymer networks transitions from solid to liquid as a result of bond exchange reactions in the network. So this rate of exchange reaction depends not only on the temperature, but also on the type of polymer, on the stiffness of polymer chains, then on the catalyst type and the concentration used. So there are different methods to measure this temperature, and one of them is through stress relaxation experiments, which I'm going to talk more later. So now more about sealants in general. There are different standards that specify what are the properties that sealant has to satisfy. We used as a reference this ASTM D5893, which is for cold apply silicone joint sealants in concrete pavements. And in this standard, it is specified what is going to be the cure, what should be the cure time, then tag-free time, for example, 5 hours, elongation, more than 600%, tensile strength. The maximum is limited to 0.3 megapascals, because in that way it is going to limit the stresses that are going to be developed at the interface between the sealant and concrete. And then there are also requirements for the durability of the bond and heat aging, weatherability. We were mostly focused on getting a sealant that can be cured in ambient conditions, that is going to be prepared from commercially available materials, and then to satisfy elongation, tensile strength, elastic modulus, and then we tested adhesion. And then the other part of the project is going to be testing durability. So to prepare the sealant, we used liquid polysulfide oligomers and epoxy resin. Polysulfides, they are already used as sealants because they have good adhesion to glass, to steel, to concrete, and then they have also high molecular weight and low degree of cross-linking, which is beneficial for cell healing and extensibility. They also contain these disulfides bonds that I mentioned that can rearrange at room temperature. So the synthesis was very easy. It was basically combining all the compounds in a cup and then mixing for 2 minutes in a high-speed mixer. Then they were poured into silicone mold and cured for 21 days in ambient conditions. We prepared several formulations and tested different variables that to achieve good required mechanical properties and optimize cell healing. So first we tested different types of polysulfide. So these polysulfides, they are prepared by a certain amount of cross-linking agents. Here they're labeled as TCP. If, for example, amount of this cross-link agent is higher, then there are more branched polymer chains in the polysulfide, and that means that if there are more cross-links, then we get the higher strength and lower and actually lower extension. But if the polymer chains are mostly linear, then we get improved elongation. Then we varied molecular weight of the polysulfides and then ratio of epoxy to thiols. And in the end, we added a percentage of catalyst to accelerate these bond exchange reactions at room temperature. And we used two different percentages, 0.5 and 1%. So to test to determine the mechanical properties, we used the tensile test and measure the strength, ultimate elongation, elastic modulus, and then cell healing efficiency was measured as a percentage of restored elongation. These are in the end adhesion tests to concrete. This plot shows all strain stress curves for the different sealant formulations, and they were also compared to commercially available polysulfides and also silicone sealants. This is green and pink color. So the range of elongations was between 100 and 900%, and the stress was between 400 kilopascals and 20 kilopascals. And here you can see how these different test variables affected elongation and strength. So reducing the cross-linking in the polymer improved elongation from 100% to almost 400%, but reduced the strength. And the same effect was when we reduced the content of epoxy in the mix. And also when we increased the molecular weight from 4,000 to 4,500, we also had a significant increase in elongation. And this is how everything compares to ASTM D5893 minimum strain requirement. So only 4 of these sealant formulations satisfy that condition. And we decided that this one is maybe the best one, because that was after conducting the self-healing experiments. So with self-healing experiments, we had just these tensile specimens cut in half, and then they were healed for 24 hours in ambient conditions. And this shows how just adding 1% of these catalysts improved the self-healing efficiency by increasing restored elongation from 400% to more than 800%. So for the adhesion test, we prepared the joint samples using 2 concrete substrates, and the cavity was formed by using this Teflon spacer, and then sealant was poured inside the cavity and cured for 21 days, also in ambient conditions. The adhesion, these tests showed that the failure is cohesive, and that maximum stress developed in the joint was 20 kilopascals. So there's some of these transportation agencies, such as Department of Transportation in Virginia, requires that this stress is at least 240 kilopascals. So that means that we are really below that, and we should make additional changes in the formulation of the sealant to achieve that. Regarding the topology transition temperature, we intend to measure this and correlate to self-healing efficiency. So for that, stress relaxation experiments were used, and these experiments were done in compression by applying 10% strain and measuring relaxation times. Relaxation times were measured based on Maxwell model, as the time that is required to relax the stresses to 37% of the initial stress. And this method, so after doing these stress relaxation experiments at different temperature, the plot that shows dependence of relaxation time to temperature was prepared, and then a line was fitted to the data. And this method, based on the stress relaxation experiment, implies conventionally assigned viscosity value of 10 to the 12 pascals times second to describe the transition from solid to liquid of the polymer. And using this Maxwell relationship between viscosity and relaxation time, we were able to calculate, we were able to extrapolate this TV temperature by to be minus 44 degrees Celsius. So this is something that we are going to continue working with it, and the 2 things that are going to be addressed are low tensile strength. That means that we have to modify the sealant formulation, and the next thing is to evaluate topology transition temperature for different sealant formulations and correlate to self-healing efficiency. Then evaluate effects of compression force on self-healing efficiency in the joint, and then see effects of moisture, UV, and motor oil on the self-healing and adhesion. Okay, that's all. Thank you.
Thanks, Sandra.
Thank you.
Could I ask you a question?
Yeah.
Okay, so I think it's rare that you see essentially when people present similar research that they are able to kind of describe the molecular structure and like kind of how this plays a role, and basically, in fact, you've gone further because you also conducted a lot of the mechanical testing and so on and so forth. And so I was curious if essentially we might be able to tie further some of the properties to the molecular structure that you showed, which basically my question is, I don't know how much room there is to design these sealants and basically designing new polymers that might perform even better.
Yeah, I think that this is now very trend in material science to design on this level and to get material properties on the bigger scale by doing modifications in the, polymers, catalysts, and the type of polymer network. So I think there is a huge potential there. And I also want to thank the Professor Kloxin, who is from material science in University of Delaware, that he's also on this project, and he's helping us with making the sealant.
Yeah, thank you. And I think that's also what I was going to say, that you rarely do you see when material scientists are doing these things. I don't know that they are considering applications at civil engineering scales. And
Exactly.
so I enjoy your talk. I think that it definitely seems like a new twist on doing these things. And
yes, there are a lot of papers written about these different, like chemists, they write a lot about this reaction is possible, but no one actually started applying this for different things. I mean, there are some, but not as much as just theoretical papers without application. So I also think this is really a good step.
Are there any other questions for
Sandra, I have a quick question. Okay, so basically the sealants, right? The product do not have 75-year service life, and I see a lot of repairs on the joints happening over the period of time. So do you know what is the current service life of the sealant, and how is the sealant that you're proposing is going to make, if it's going to make any difference to that? Because it seems like if it's self-healing, then it probably have more service life to that, right?
Yes, it is now, service life is about 10 years. And this one, I mean, we can just assume that it's going to improve, but that's the idea. Basically, for example, in the joint, during the summer, like when the temperature increases, the joint is going to shrink, and that is going to apply pressure on this self-healing sealant. So if there is a crack inside, then these two surfaces where the crack is are going to close, and then these bonds can reform, and that's basically self-repair that we want to see.
And another question, just addition to that, I think you have discussed about how is it applicable to the DOTs, but I really also see the application of this in the building industry as well. Do you have any plans on seeing how does it comply with the building industry as well?
Yeah, it is possible to, to all these other types of. I don't know much about buildings. That's not part of the project, but definitely it can be used for that.
Okay, that's pretty much it. Thank you, Sandra.
So on this, actually, I just wanted to make sure that I understood. You said in one of the experiments, you cut one of the samples in half. Mm-hmm. And I'm assuming that you cut it in half, and then the bottom picture is it healing, like after having done some healing?
Some of them, they don't look like this. Okay. They don't heal completely. There you can still see, for example, the scar from the cut. But basically, this one, when we add 1% of this catalyst, sometimes I don't even see the cut. And when I retest everything, it doesn't fail at the same section, it fails somewhere else. So
wow. Okay. And so when you put it to reheal, did you put it under compression as you were just describing, like as might happen in the summer, or just?
I just have these molds with the and then I replaced both halves inside the mold, so I don't apply much pressure. They're just in contact in the mold.
Yeah. Okay. Wow. And I just find this really fascinating. So, how long is it after the 24-hour period that it kind of came back together? Or
well, you see here, for example, after, I think this is after 2 hours, we had already above 600% strain that was restored. After self-healing, only 2 hours. Yeah.
Yeah, really, really impressive.
Yeah, thank you.